My name is Noam Levine from MathWorks, and I'll be presenting this session titled MATLAB and Simulink for Communication Systems Design. In this session, we'll learn how to accelerate system development in general using model-based design methodologies, how to apply a model-based design approach to a specific communication system example, and then take a look at automatic code generation to implement our example system on a hardware platform. The platform we'll be referencing is the Zynq 7000 SoC Analog Devices Software-Defined Radio Kit from Avnet Electronics. One of the main challenges in designing and implementing systems designs efficiently is the lack of a direct connection between algorithm design and hardware implementation. It can be hard to verify operation on chip against algorithm specifications. If errors exist, or if the system does not perform as expected, it can be difficult to determine if the fault is due to algorithm issues, hand coding errors, or other hardware issues. The time spent in trying to identify the source of the issue and then fixing it can be very costly. With different teams potentially involved in the hardware and software design, you can end up with different test benches for hardware and software that may not match completely and may get out of sync with the overall system specification requirements, particularly if those requirements change over time. Is there a methodology for tracking specification updates and ensuring that the coding efforts are keeping pace? To address these challenges, we'll look to model-based design with MATLAB and Simulink. As we'll show in this session, model-based design provides a common platform and unified design environment for algorithm design, simulation, validation, implementation, and verification. Model-based design provides an integrated workflow which can lead to increased collaboration across teams as everyone is working from the same MATLAB and Simulink-based executable specification. You begin with your system requirements and research, which starts the design process. Through careful system-level modeling, your requirements become an executable specification to design against. Any changes that may occur in requirements and specifications as the project moves forward gets reflected at this model level. By making design changes only at this level, the rest of the process is guaranteed to stay in sync with requirements. Verify the system model at this level to confirm that it meets requirements. Tests you develop to verify the model against specifications now are the same tests you will use later in the design process to verify your implementation. If requirements change, you just need to verify that the system model meets the updated requirements at this level, and the changes will flow down through the process. Implement the algorithms for hardware target like the Xilinx Zynq All-Programmable SoC through automatic C and HDL code generation from your executable specification, which is your Simulink models and MATLAB code. At this stage, you can verify that the code works on the platform through hardware-in-the-loop testing using the same test bench you use to verify the model itself. Performance data at this stage feeds back into the system model design. Is the fixed-point implementation providing acceptable numerical performance when compared to the specification? If not, can fixed-point parameters be adjusted in the model so that the implementation meets spec? Is the FPGA throughput and resource utilization acceptable? If not, can Xilinx-specific IP blocks be inserted into the model to optimize FPGA area and speed? Are the tasks being performed in the right resource? Would repartitioning tasks between the FPGA and ARM on the Zynq achieve the desired result? Do you have legacy code whose functions you would like to incorporate? Automatic code generation and project automation makes design iteration fast and reliable, and allows you to explore a range of design options and optimizations without breaking the design flow, so you don't inadvertently introduce errors during this phase. Finally, you can deploy your design on the target by integrating any platform or device-specific components, and again, verify final operation to system specifications. Let's now look at some of the details of each of the steps in the model-based design flow as they relate to implementing systems on the Xilinx Zynq SoC. In the design phase, you can access an extensive library of existing IP from toolboxes and block sets for signal processing, communications, motor control, image and video processing, along with models of specific analog and RF components that allow you to fully simulate the operation of your system. Within the Simulink modeling environment, you can use the MATLAB language for scripting, testing, debugging, and algorithm development. To tune performance, you can incorporate Xilinx system generator IP targeted to specific devices, or you can import custom IP in C, C++, or RTL. In the implementation phase, you can explore design partitions between hardware and software components and tune different performance parameters. The coder tools automatically generate the appropriate AXI-P core for the FPGA to communicate with the ARM. For improved firmware performance, generic C code can be replaced by ARM9 Neon instructions automatically. For a Zinc workflow, we can automatically generate an interface model that allows the ARM processor to communicate with the FPGA. HDL Coder supports automation scripts for system assembly in Xilinx Platform Studio, BitGen, and for device programming. And hardware-in-the-loop simulation capabilities exist to verify system design performance on the target platform with real-world data, either with free-running clocks or synchronized to the model. Finally, Simulink and coder tools are integrated with the Xilinx toolchain to make it easy to iterate designs on hardware. Now we'll take a look at how we can apply a model-based design approach to communication systems targeting the Zinc SDR platform featuring the Analog Devices FM-Comms FMC module. This slide shows the design flow for a communication systems example targeting the Zinc SDR platform. We'll start with our algorithm model built using a combination of MATLAB, native Simulink blocks, and Xilinx system generator blocks, and verify its operation simulation. We'll then generate HDL code, which gets fed through the Xilinx Platform Studio environment, where we can verify performance through Simulink with code running on the target. We can then integrate with code running on the ARM, from which our first stage bootloader and FPGA programming files are generated to load on the board for standalone operation. In this session, we'll just be looking at the algorithm verification through simulation and the HDL code generation parts of the workflow. To build and verify our algorithm, we can access Simulink block sets for signal processing and communications, models of specific RF components. We can incorporate MATLAB functions into Simulink blocks and implement visualizations and graphical interfaces to adjust system elements. In this session, we'll look at a part of our SDR system, specifically the QPSK symbol timing generation and digital up converter pieces of the transmitter, and the digital down converter and symbol timing recovery pieces of the QPSK receiver. In Simulink, the system block diagram that we saw in the previous slide would look like this. And now, let's go over to Simulink and start exploring the model. Here we are in Simulink, ready to perform algorithm validation in simulation. But first, let's explore the model. Here, we see the transmit section, which generates QPSK symbols starting from a pseudo-random sequence generator. The transmit then goes into what's called a digital front end. We have limited this to a single root raised cosine or channel filter. This is basically a low-pass filter that shapes the square QPSK pulses and limits their bandwidth so that we can transmit them over the air. Now let's look at the receive section. Here we are in the DFE of the receiver. It also has a root raised cosine, and the combination of those matched filters, the one here in the receive side and the one in the transmit side, if you convolve those two filters in the time domain, it equates to a multiplication in the frequency domain, and the two together create a composite response of a raised cosine filter excellent at mitigating intersymbol interference. Notice too that we've added a spectrum scope after the incoming symbol so that we can take a look at the spectrum of the matched filter. Finally, we have the symbol timing recovery loop. If we look inside there, we can see our Faro filter. And from the symbol timing recovery loop, we're going to use HDL Coder to generate HDL for this part of our design. Out of the symbol timing recovery block, we're taking strobe and we're going to be looking at our symbol data so we can visualize the received signal in a scatter plot, and that will give us the quality of our receiver using what's called EVM as a measure of separation of the symbols on the scatter plot. As the first step in making sure that our system is going to work properly, we're going to verify our algorithm operation in simulation. So I'm going to launch simulation. And we're going to take a look at our system visualizations. Notice the sharp roll-offs of the frequency spectrum, which would allow subsequent decimation stages typically found in a digital down converter after the matched filter, although we haven't included any further decimation in this model. Also notice how the QPSK symbols are well separated on the scatter plot, which would ease the subsequent demapping of the symbols back into the data bits of the payload. So we've now confirmed that our symbol timing recovery algorithm is functionally correct. However, a real communication system includes data converters as well as the accompanying analog circuitry, including RF transformers and analog filters. The analog signal is also affected by the channel, whether over the air or even just looped back through cables, as we're doing in this demo. Furthermore, the interface between the FPGA and the data converters must be designed, which is not a small task for the high-speed data capture of hundreds of megasamples per second. Presently, none of the effects has been accounted for in our Simulink model, but those are certainly elements that can be added to the model for a more detailed simulation. Now that we've verified that our algorithm works in simulation, the next step in our system development process is code generation. Both Xilinx System Generator and Simulink have powerful automatic code generation capabilities that can be combined in a common model-based design workflow. Let's first discuss some of the merits of automatic code generation. Automatic code generation provides a continuous tool flow from algorithm design to implementation. It can eliminate any errors that can come in as a result of hand coding HDL to a paper specification. As we saw earlier in our model-based design workflow, maintaining your top-level system models as your executable specification means that any spec or model updates are automatically accounted for with automatic code generation. And finally, automatic code generation enables fast deployment on hardware, as you can go directly from model to HDL code without having to wait for hand coding. Our system model contains both Xilinx System Generator and Simulink blocks. Let's see how these can be used together. Using both Xilinx System Generator blocks and HDL Coder from MathWorks plays to the strength of both tools. With HDL Coder, you get access not only to the algorithmic base of native Simulink blocks, but you can also generate HDL directly from MATLAB. Using HDL Coder, you can utilize the abstract data types and floating to fixed point conversion capabilities of Simulink, along with flexibility to perform design exploration and model elaboration. HDL Coder also provides code-to-model and model-to-code traceability, useful for design reviews and where standards compliance is required for design certification in certain industries. With System Generator, you get access to device-specific implementations, allowing you to tune system performance where necessary, along with hardware co-simulation functionality and the ability to gain access to analog I/O to acquire real-world data for further design exploration and validation. Now let's take a look back in our Simulink model and see where we've used Xilinx System Generator blocks and where we've used native Simulink blocks in our design. In this particular design, our QPSK generator and both DFEs were done in System Generator blocks. And we can take a look down into those elements. These System Generator blocks will correspond to specific HDL implementations for the Xilinx Zinc SoC. Take a look at some of our filters here. and in the DFE as well. Our symbol timing recovery, however, was done in native Simulink blocks. The interface between the Xilinx system generator blocks and our native Simulink blocks are done with these gateway elements. So there's a gateway out that goes between our receive DFE and our symbol timing recovery loop. So our symbol timing recovery loop, this is all done in native Simulink blocks. So we're going to use HDL Coder from MathWorks to generate HDL from our symbol timing recovery loop, and System Generator for DSP from Xilinx to generate HDL from the other elements that were done in System Generator blocks. Now let's take a look at the HDL code generation process for our symbol timing recovery loop. To start the process, we're going to invoke our HDL Workflow Advisor. The HDL Workflow Advisor provides a step-by-step walkthrough of the HDL code generation process. To start the process, we're going to set our target device. For this example, we're just going to generate HDL code, which is going to be later exported through the Xilinx toolchain for deployment on the target. We can then prepare the model for HDL code generation. This part of the process does a number of checks on your model to make sure that it's ready for code generation. So we're just going to run all of them. Now that we know our model is ready for code generation, we're going to generate the code. The HDL code generation process gives you a number of options depending on what sort of quality of results you're looking for your generated HDL code, whether you want to optimize for speed or area or other constraints in your system. So let's go ahead and generate our code. Now that our HDL code generation is complete, we can look at the code generation report that's automatically generated by HDL Coder. This report tells us the outcome of our HDL code generation. We can get a review of our clocking. We can take a look at the types of resources that are used in our programmable device. And we can also take a look at traceability. As I mentioned earlier, one of the things that HDL Coder gives you is model to code and code to model traceability. And this is useful not only for design reviews, but also if you have any standards compliance issues that you need to worry about. So let's take a look at that. If we look at our Faro fractional delay, for example, that we saw earlier in when we were looking at the model, this is the HDL code that was generated from that Simulink model, and you notice that this is readable code. This code also has a number of hyperlinks in it, so when you click on any of these, it'll take you down to that model level, and so you can see exactly what block in your model generated that line of code. Similarly, I can go to any block in my model and navigate to the code. What we've covered so far has been a look at system development with model-based design. We've taken a look at algorithm verification through software simulation, and finally we've just seen automatic code generation for FPGA and SoC implementation. Hopefully you've seen how a model-based design flow with MATLAB and Simulink can help speed your development process. This seminar really only scratched the surface of what's possible with model-based design for communication system development. So here are some topics for further study that we'd be happy to talk to you about at the MathWorks booth in the exhibit area. Through the use of physical modeling tools like SimRF, you can actually develop accurate models of specific RF and analog interface devices, such as those found on the ADFM-Comms FMC module. With a library of device model blocks, you can quickly determine which components are going to work best in your system before you even build your first prototype hardware. The workflow that we've been showing so far in this session has really only targeted code generation for the FPGA side of the Zynq SoC. MathWorks has recently introduced a hardware-software integrated workflow for the Zynq 7000 SoC that not only does code generation in HDL for the FPGA side of the Zynq, but also includes automatic interface model generation and C code generation using embedded coder to target the entire Zynq SoC device. We also didn't get an opportunity to go into hardware co-simulation to verify algorithm operation with real-world signals, or HDL code verification and FPGA in-the-loop test benches. For more information on model-based design for communication system development, you can visit MATLAB Central, where you can find both user and MathWorks staff contributed articles and examples for communication systems. The MathWorks book program has a number of titles on communication system design with model-based design. And in our communication system toolbox product, a number of demos that highlight a model-based design approach for communication system design. In North America, a complete hardware-software FPGA DSP development package is available with either annual term or perpetual license options from Avnet Electronics. Visit www.em.avnet.com/ADI-ZynQ-SDR to learn more. We're now ready to open up the floor for Q&A. So please go ahead and ask any questions you have about model-based design for FPGA or Zynq development. Thank you for attending.